Okay, continuing on today with our Laplace transform playlist, we finally start to see some payoff from everything we've done because we have here a differential equation. We have here the differential equation y prime plus 8y equals e to the minus 4t. And we're given this initial condition over here to the right that y at 0 is just equal to 1. Okay, so like I've mentioned in previous videos, probably the most common use of Laplace transforms is in solving differential equations. So we're going to start with a pretty simple differential equation. And now for this particular example, you could solve this other ways pretty easily. I expect to do a differential equations playlist coming up in the future, but for now we'll just focus on how to solve this using Laplace transforms. So our goal in doing this is to get a solution that involves no derivatives. So what we can do in this case is actually just isolate y. So if we can get a solution for y in terms of t, then that's all we need. And now you'll notice that our equation has a derivative in it. So what I've already done is copy down our Laplace transform for y prime of t. So a quick note on this, if you go back to the video that I did on Laplace transform of f prime of t, it's the same formula, but here our variable is going to be y. So we have y as a function of t, and so this is what we're going to use for this. And so this big y of s is like our big f of s. So this big y of s in our formula, this is going to mean the same thing as the Laplace transform of y of t, but we can just leave it as y. And this y when t is 0 condition over here, this is given to us as our initial condition, so we have that right there. So this value is going to be 1. So to get into our solution for this, our first step is going to be just taking the Laplace transform on both sides of the equation. So this is going to give me Laplace transform of y prime plus 8y, and it's going to be equal to the Laplace transform of the right side, which is going to be e minus 4t. But then, like we've gone over previously, I can split this on the addition sign, so I can write this as Laplace of y prime. And for this one, I can factor the 8 out front, and we can write this as Laplace of y. And then here we can just take the Laplace transform. We have this formula we went over previously for the Laplace of e to the at. This is going to be just 1 over s minus a. So for this thing, we end up with just 1 over s plus 4. But now for this right here, we can just apply the formula we discovered earlier. So this is just going to turn into, on the left side, this is going to give us s, big Y of s, minus y of 0, but we know that value to be 1, so I'm just going to write that in as minus 1. And then this here is going to be 8. And what we determine right here, Laplace of y is just going to be our big Y of s. And then we'll copy this down right here. Now, like I mentioned initially, our goal here is to isolate y. Well, we don't really have y here, but we have this big Y of s, but that's going to get us pretty close because then we can get it where we can just use the inverse Laplace transform if we get it here. So what I want to do is just solve for this. That's going to be our short-term goal, just to isolate this thing. So what I'll do first is let's get rid of this 1. I'll add 1 on both sides. But over here, when I add 1, I want to get a common denominator, so I can write this 1. I'll write it as s plus 4 over s plus 4. And now we have our big Y in common over here, so we can just factor that out. So we'll write this as big Y times s plus 8. And then over here, we'll combine terms. So we're going to have s plus 4 here. Then we'll have s plus 4 plus 1. So this is going to give me s plus 5 here. But then I can divide by s plus 8 on both sides just to isolate this again. So we'll divide it over here on the right. This will cancel out. And now we've isolated our big Y right here. But now this is pretty good, right? Because this, again, just to make it clear and reiterate, this is Laplace of y. We want to isolate y. So what I want to do then, if I can just apply the inverse, if I apply the Laplace inverse on both sides, apply, I know I'm kind of out of space there, but we apply the Laplace inverse here and here, what's going to happen is this is going to essentially cancel out, and now we've isolated our y. So now all we need to do in order to solve this thing is we just need to do an inverse Laplace transform. You'll notice we spent a lot of time on the inverse Laplace transform in the previous few videos. That's because in doing a differential equation, what it comes down to in the end is solving an inverse Laplace transform. So let me clean up the board, we'll do this thing and finish it off. Okay, now just focusing on the Laplace transform of this thing right here, you'll notice it's not really like anything in our Laplace transform table. So I don't have a quick, really simple way to do this, but what we can do is use partial fractions on this. So let's kind of come down here and work on our partial fractions. So we'll rewrite this fraction. In this case, I can use the cover-up method. We'll just split it on s plus 4 and s plus 8. So my first term we'll write as a over s plus 4, and the second one b over s plus 8. So we're just going to want to solve for these constant values, a and b. So for the cover-up method, what we'll do, starting with what makes this 0. If I say s equals minus 4, cover up that part so we're not dividing by 0, but then plug in the minus 4 everywhere else. Starting in the numerator, minus 4 plus 5 gives me a 1. And then here, minus 4 plus 8 gives me a 4. And so this a value is just going to be 1 over 4. Then doing the same thing on this second term, which we've associated with b, just want to notice that s equal to minus 8. Plug that in there, that's going to be a 0. So we cover it up, but just plug in for s everywhere else. So here, let's see, in the numerator, minus 8 plus 5 gives me a minus 3. And here, minus 8 plus 4 gives me a minus 4. But minus over minus gives me a plus, so our b value is just 3 over 4. So now that we have our a and b values, we just need to take this and plug it back in here into our inverse Laplace transform and rewrite this. So because we have a plus sign here, I'm just going to right off the bat split this into two pieces. So the first one will be this 1 over 4, s plus 4. And then the second one is going to be this 3 over 4 and our s plus 8. But then we have constants here in the numerator, so I'm just going to factor those out really quick and rewrite this. But now we just have two inverse Laplace transforms that we know how to do, and we're going to just use this formula down here to the right that we actually used earlier. And so in this first case, our a value, this is going to be minus 4 here, because if you plug a minus 4 in there, you get the s plus 4, and this one's going to be, our a value is going to be equal to minus 8. So using this and putting it all together, what we end up with is we'll have our 1/4. For the inverse, we're going backwards and using this a value, so this is going to become e minus 4t. Then for the second term, we end up with 3/4 e minus 8t, and that's it. Okay, now just to sum it up, what we did here is we found this to be our y value. That solves this equation here. And so what you may be wondering is if we plug this back in, does it all work? Can we show that this is equal? Let's just do it really quick. So we have our y value. Let's look at our y prime value, just taking the derivative here. Derivative of this, derivative of the first term is going to be minus e minus 4t. Derivative of this second term is going to give me a minus 6 e minus 8t. Now the other part is 8y, so let's just take our y and multiply it by 8. So 8y is going to be 8 times 1 over 4, that's going to give me 2e minus 4t. Multiplying an 8 here, this gives me a positive 6e minus 8t. If we just add this together, this here is the left side of the equation. So if we add this together, these two terms are going to cancel. 2e minus 4t minus e minus 4t gives me e minus 4t. And that's the same thing we have right here on the right. Okay, so there you have it, solving a differential equation using Laplace transforms. And I said I wouldn't really compare methods, but the one thing you'll notice about this is it was all algebra. We didn't have to integrate anywhere. So that could be useful, right? Because if we ended up with a differential equation with complicated integrals, we're able to sidestep that with the Laplace transform. But just be aware that in some cases it's going to actually make it worse and make it more complicated. But I would say it's going to help us in some cases, and it's another tool or method that we have when we're solving differential equations. Okay, so that's it, but we'll do a few more differential equations in the upcoming videos. Thanks everyone for watching. Have a good day.